Hi, this is Raf Alvarado and welcome to Exploratory Text Analytics. In this video, we're going to look at how to infer language models from data, specifically the kind of data that we've already looked at in the last two modules, where we downloaded the text and then we were able to convert that text into a tokenized data frame that reflected the ordered hierarchy of content objects model. Before we get started, though, I think it's a good time to introduce a concept that we're going to be using throughout the course. It's a term that in the past I've assumed that students understand, but actually it's something that should be mentioned. And that's the type and token distinction that comes from the text analytic tradition. I'm not sure actually whether it was invented by NLP or whether it was invented by computational linguistics or information retrieval. But essentially, the term is used to describe what we have been describing in Shannon's case as a symbol set and a sequence. So a type is very much like a class in object-oriented programming or in logic. It's a class of symbols, and so a type is a member of a distinct symbol set. So it's a distinct member of a symbol set. So this is, a classic example of this is an alphabet, where you have one instance of each letter. It is the basis from which you select letters to create a sequence, say. So a token is an instance of a symbol. So it's a copy, if you will, from a list of distinct symbols in the type set. And it's what actually appears in a text, where you can have the same symbol repeated and distributed according to how it's been employed in the message. So it's a very simple distinction, but it is also a specialized vocabulary to talk about this kind of thing that gets talked about in different ways. It's also important to understand that the word symbol in this context means a material reproducible sign, such as a letter or a word. It can be a letter, it can be a word, it can even be a sentence. Basically, what a symbol is in a symbol set is something that can be defined by context. We often say, when we're talking about word tokens, we often use the word word to describe a word, or the word character to describe a character. And when we do so, we often conflate the distinction between the word type and the word instance, or the character type and the character instance. It's often important to understand this distinction, but at the very least, it's also important just to know what these words mean when I use them going forward. So today we're going to look at language models, and this is all built, as I've said before, on Shannon's mathematical theory of communication, which I asked you to look at and read the beginning of. Shannon's insight, to repeat what I said last time in a more succinct form, was to think of messages as having a probability. It's basically the main idea is that every message that is emitted from an information source, that is to say every sentence that is produced by a speaker, say, has a probability value. And the information of the message is inversely proportional to its probability. And that's essentially what the entropy function builds on, is that fundamental insight and that fundamental relationship. Now, the probability of a message can be computed by mapping its elements onto a language model. Now, this is different than computing the entropy of a message or the entropy of an information source. It's obviously related, but this specifically is just, let's compute the probability of a particular message. So if we have a message M, that consists of a series of symbols, a series of tokens, and we're representing those as S1 through Sn, where n is the length of the message. So the probability of a message is just the joint distribution of its tokens. Now, Shannon provided a bunch of models for how to account for that probability, these generative mechanisms that one may use to more and more closely approximate a natural language like English. He called these finite, he didn't say machines, but finite systems, I believe is the term he uses. But nowadays you'll see these described as finite state machines. And he went from the simplest one, which isn't listed here, of every letter having the same probability, to these listed here as levels 2, 3, and 4 of increasingly complex systems that generate speech based on what he called the Markov model, which we're going to see today as the Markovian assumption. So the overview is this. Today we're going to look at the concept of language models as inherited from NLP, inherited from Shannon by NLP. And we're going to look at these models because they perform a lot of work within the general field of text analytics and all the other fields that text analytics is composed of. So language models are used to predict discourse, for example, in the case of Siri and Alexa and so forth. They are meant to be as general as possible, to be applicable to future discourse events, again, like when you're interacting with a data product like Alexa. They're also designed to help identify language features such as part of speech, named entities, grammatical dependency, etc. So this is really important for us because we're going to take advantage of libraries that use language models to provide this added value to our texts once we encode them in the data structure that we looked at last week. We're going to add more data to this data structure based on the work of NLP libraries that at root take advantage of language models. But we also want to explore them in detail, even though we're going to use libraries such as NLTK that make use of language models. We want to explore them in some detail because we want to understand what we're actually using when we use them in our text mining or text analytic applications. We want to get under the hood and see what's going on there. This is going to be helpful also when we look at particular models like topic modeling and so forth, where in effect what those models produce are a bunch of language models. And once you see that, it really helps you understand what these particular techniques are trying to achieve. So what is a language model? As I described earlier, it basically models the probability of a sentence, which is to say it's the probability distribution over token sequences in a sentence. So here we have a couple of sentences with some probability values that have been assigned to them. These aren't real, but they're sort of on the order of magnitude that you might imagine. What's the probability of the sentence today is Wednesday? It gets a relatively high probability relative to the next sentence, which is today Wednesday is. And notice here, the order of the sentence matters because we're talking about the sentence itself in lump as the symbol. So we're looking at this sentence, today is Wednesday, versus all possible sentences. And so today Wednesday is gets a very low probability because the only people that speak like that are perhaps Yoda from Star Wars. A sentence like eigenvalue, the eigenvalue is positive, gets a lower probability than the first and higher than the second because it is uncommon generally, but perhaps very common within a particular speech community, say the speech community of data scientists. Now, a language model can be both descriptive and prescriptive. It can be descriptive in the sense of being derived from a corpus through frequencies, which is we're going to look at today, or it can be prescriptive. Once you have the model, it can be used to generate text, as with the sample method in Pandas, which I'll show how that works in our code walkthrough. So how does a language model help us in the NLP tasks that we described earlier? Here's some specific cases. So in the case of machine translation, of spell correction, and in speech recognition, in each case you can see that often it reduces to picking a sentence with higher probability. So how do we calculate these probabilities? Let's go over this. The probability of a sentence, for example, of 5 words can be represented in this way. I drove to the store could be a sentence, and we're going to represent that as a sequence of 5 words or tokens, let's say. Word 1 through 5. The probability is just the probability of that sequence. The probability of a next word, let's say, can be modeled as a conditional probability of a given word given the words that preceded it. So let's say we're trying to model predict the utterance of the word store, given that I've already said I drove to the. So that's basic conditional probability, and it can be expressed in this particular formula where you have the joint distribution of everything divided by the joint distribution of the antecedent, the words minus the word that you're trying to predict. How do you calculate these sequences? Well, we use the chain rule for probability whenever we have a sequence of this kind. So the probability of a sequence of tokens or a sequence of events is the probability of that sequence of events given the prior sequence iterating through I, as we can see here. Here it is fully expressed. The chain rule generates this particular equation. The probability of, word 1, word 2, word 3 in sequence is equal to the probability of word 1 times the probability of word 2 given word 1 times the probability of word 3 given word 1 and word 2 times the probability of word 4 given word 1, word 2, and word 3, and so forth. That is what the chain rule prescribes, and that, you can see, can get complicated fairly quickly if we're trying to compute the probability of longer sentences than this. What's the problem with this approach? It's too hard, as I've said, to compute for long sentences, especially considering the full history of a word in a text. If you really wanted to incorporate full context, a word being used in a particular text where you want to include everything in the chapter or even the whole text leading up to it, you're going to end up with some very, very complicated problems or equations to solve. So we make an assumption that I mentioned earlier in this presentation to simplify our computation of probabilities, and that's called the Markov assumption, which is an assumption that we saw Shannon made use of in his paper. When you choose the Markov assumption, you only consider a small number of previous events when computing the probability of an event. Instead of including all previous words up to a word, you usually pick only the first word preceding, or maybe the first or second word. Here's how it looks in practice. So instead of trying to predict store based on I drove to the, you predict store based on the. That's called a bigram model, because it's just looking at two words or 2 grams in its distribution. How many times does the word store, is it preceded by the word the? A trigram model would say, how many times do you find the word store preceded by the 2 words to and the? And here they are expressed mathematically. Note that in the antecedent here, for this probability statement, the subscript is used to signify the offset of the start, and the superscript is used to signify the offset of the ending word, and that's actually a list. It's not a single value here. So for any given sentence of length n, this is going to be the equation you use to compute its probability. Simplifies things a great deal. So question then is, how do we discover these values, probability of a word given the probability of its previous word? We have no real place to go to get these data. We don't actually have access to an actual language model out there in the world waiting for us. So we have to infer it. We have to construct it from our data. And our data consists of the text that we have before us. We use something called maximum likelihood estimation to get this data just by observing the relative frequencies on a representative set of sentences, and we use these as estimates of the real distribution. So let's see what that looks like. So the law of conditional probability says that the probability of B given A equals the probability of A and B over the probability of A. So if we want to compute the probability of B given A for any given pair of words in a corpus, what we do is we count the number of times the 2 words exist together, and then we divide that by the number of times the antecedent word or the first word exists by itself, independently of whether it exists with that word. So it's the total number of times a word exists as the denominator, and the numerator is the total number of times that word exists followed by that particular word. You can see that the top is always going to be greater than or equal to the bottom, very often, typically much less frequent than the bottom. Unless you're talking about something like, say, let's look at characters. The probability that U follows Q is going to be really high. The frequency of the letter Q in English is almost going to be about as frequent as the letter Q followed by U. But cases like that are pretty rare, but they do exist. In pandas, we can compute this value pretty quickly by using the group by function on a data frame of bigrams, which I hope to be able to show you. So how do we create a bigram model in order to find these data? Okay, so here are some data from which we can infer a bigram language model. This is actually data from the Berkeley Restaurant Project, which Jurafsky and Martin refer to. This is a subset of that data. They've selected some words that have a pretty high co-occurrence rate. If you looked at the entire data set, all the words and all of their co-occurrences, it would be a pretty sparse matrix, mostly zeros. So the top table just refers to the marginal distributions or the prior distributions of each word in the corpus as a whole. The second table shows the raw counts of the co-occurrence of these terms with each other. So it turns out that, for example, the word I follows the word I, 5 times. That's some anomalous behavior, but it happens. More frequently, you'll see the word want followed by the word I, as in I want, or want to. You'll see that frequently, to eat, and so forth. The table below it is a normalization of the table above, where every raw count is divided by the prior on the left side, as it were. So, for example, in the cell I want, which has a count of 827, the value 0.33 in the second table is achieved by dividing 827 by the count of the number of times I exists, 2533. So there you have a table of frequencies for bigrams. So what do you do with this information? Well, you apply it to a given sentence that you find. So let's say you find the sentence, I want English food. What you do is you divide that up into its constituent bigrams, where we treat space as a token. And so the first bigram is the word I preceded by a space, and then we have the word food preceded by the word English, and so forth. And each one of these has a value in our lookup table that we just saw. Imagine that table expanded. And by multiplying all of these together, we get a total probability. That's the estimate of the probability of that sentence given that language model. And if you're comparing two language models, well, you'd go for the language model that provides the highest probability for that sentence if you want to try to figure out what generated the sentence. So how do we evaluate our model? Well, there are a couple of things we can use. One is the cross-entropy measure, which can be expressed as a perplexity, and then we use this perplexity value to compare to other models. And just as in a supervised learning pipeline, we're going to divide our corpus into training and test sets, and then we're going to generate both models from the same training set, and then see which one produces the highest probability for a given sentence. So even though we don't have labeled data, we can train our data and test our data. And we also can evaluate the performance of our data, of our models, using this measure of perplexity, which is a preferred measurement technique for unsupervised tasks in the text mining space or text analytics space. So just as a side note, creating language models is very useful because it helps create products that require language prediction, as we talked about earlier, things like Siri and so forth, and spell checking. But I want to also point out, in the spirit of this course and why we're pursuing unsupervised methods and why we're looking at the concept of a language model, we want to use these things also to help us gain cultural insights. For example, if we generate a language model from a corpus of movie reviews, we may discover some interesting facts about people's perceptions of movies. If we compare a language model generated from movie reviews, say from a language model generated about wine reviews or generated from a corpus of wine reviews. In general, when you compare language models across different corpora, you're gaining insight into something about the cognitive models that generated those texts. So let's look at a more technical problem, a practical problem of generalizing a language model. For one thing, you are when you generalize a language model, you may be working on the assumption that you're developing a model of, say, English. But English, as we know, is not really as coherent a thing as we may imagine. There are many kinds of English. There are different national traditions of English, say from Wales, Scotland, India, South Africa, the United States, different regions within these countries. Each one of these has something more than an accent. These regions have what linguists might call variants of the language. And when you develop a language model, they're going to be sensitive to the word distributions and the grammatical properties of those variants of a language. So it's important to understand that that when you're comparing, testing a language model, that you test it within its target genre or its target area of application. Don't expect the model to be universal. There are also, there are also constraints of genre and historical constraints, in addition to the ones I just described that might be described as cultural constraints. And we can take advantage of this, as I mentioned earlier, because by comparing language models and comparing differences among language models, we're actually uncovering interesting cultural facts, patterns about language use that may shed light on historical change and cultural difference. We saw some of that earlier in our first module on the Culturomics School, who were able to make some interesting observations about the history of language and the history of culture just by observing changes in the usage of bigrams or n-grams over time. So some standard methods for approaching the problem of incompleteness, where you have missing words or missing combinations. Two of these are smoothing and discounting. So in smoothing, we simply add a value to zero values in our language model. So any word that has zero probability gets a probability of some very small value. Similarly with combinations. With discounting, there's an interesting notion of just shifting the probability mass from some of the higher frequency words to some of the lower frequency non-existent words from our model. These are pretty interesting and somewhat sophisticated methods. I invite you to look at the text. I list 4 of the methods here: Laplace or add-one smoothing, add-k smoothing, something called stupid back-off, and Neisser-Ney smoothing, and discounting is also part of the Neisser-Ney approach. So again, these are interesting approaches to solving this problem of incompleteness. Another approach I'm not mentioning here is something called the hashing trick, where you assign words. Basically, you convert all words in your vocabulary into a hashing function, and any new words get a hash as well. And if those new words collide with old words, well then, so be it. We're not going to go into that though, but just so you know that there are lots of methods out there to dealing with this fundamental problem of incompleteness.